All right, hello, welcome back. So far we have looked at the basic definition of what a transfer function is. And now let's look at how we can use it to do actual useful stuff. Something happened. Um, so here I have made a totally made up system. I have this mass spring system. The motion somehow opens a hydraulic valve, and that actuates a hydraulic jack. The jack opens a gate and lets the water flow into this turbine. Turbine turns a generator. Generator creates voltage, and that powers the wheels of this cart. A totally messed up and random system. Probably nobody will ever design that, but nonetheless I could imagine it. So analyzing the system, how the behavior changes on its own, looking at the entirety of the system, is probably daunting and maybe a bit difficult to start working with. But the way I described it, so the output of one system is the input to the other subsystem, and so on. So now let's look at the practical aspect of it. That imagine I have a big system comprised of many smaller subsystems, and I have each of these subsystems, for instance, each of them are described by a different transfer function. So my subsystem 1, G1 has y1 over x. My second one, G2, is y2 over y1, and so on. Maybe I have n of those, yn over yn minus 1. So if I want to know what is my final output in relation to the first input in this example, what I can do, I can start really very simply multiply all of these together. So yn over my x, for instance, I can write it yn over yn minus 1 times yn minus 1, yn minus 2, dot dot dot, no product, until I reach y1 x, and they all cancel out. So I should be able to find my yn over x to be just multiplication of all of these. Let me write it backwards. So it makes more sense. Gn times Gn minus 1 times all the way to G1. So this is one of the beauty or usefulness of working with transfer functions, that if I have different pieces of my larger system described by their own individual transfer functions, the overall dynamics of the system is just a combination of those smaller subsystems combined together in a way that is compatible with the structure of the system. So if all of them are stacked one after another, we can do this. But it doesn't end there. So it is possible to have more complex system that is not just one subsystem one after another. There could be more complex structure within the system. And we can easily try to describe the system using something called block diagram. So in this case, if I want to represent this cascade of transfer functions from some input to the output. This is how I would graphically describe it using a transfer function. First of all, any transfer function, I draw it with a block, and often I write the name of that transfer function, and it receives input x and gives output y or y1. What this graphically means is exactly this. It means y1 equals g1 of s. Let's skip that. g1. So everything is in Laplace domain. So I skip s, y1 times x. So this is the graphical representation of the same thing. And if I want to represent this concept, a cascade of inputs, I can do this. X goes in through G1, gives me Y1. Y1 goes to G2, gives me Y2. And all the way, what was it? Yn minus 1 goes to Gn, yes, gives me Yn. So this is the graphical representation of the same thing. What it means, I can kind of simplify that as x goes in, Yn comes out, and they all multiply together. So this G is G1 times G2 to Gn. So with this concept of graphically representing essentially a dynamical process, remember these are the dynamical processes that we are representing in Laplace domain. In this domain, you can see it's very easy to represent those through this relatively simple graphical representations. We can also expand this graphical tool set. For instance, I can have one input. Let's call it x. What do I call it? X goes in. I can branch it off. This one comes to, for instance, G1 gives me Y1. G2 gives me Y2. So this is a branching off kind of operator. There is also one very common graphical aspect or graphical way to show it. So I have, for instance, x1 and x2. These two can add together, go to some transfer function, and I get y. And what this represents is y is g of x1 plus x2. G times x1 plus x2. So with these very simple ways of showing graphically the concept of a dynamical system, branching off from one input and then addition of some inputs or addition of signals, I can really build very, very, very complex representations for virtually infinite complexity systems. So I think that is maybe not enough to start writing here. So have this, let me clean the board, and I will come back soon with um, some examples how these can effectively be used. Now instead of that weird, uh, really non-realistic system, let's look at something that is actually extremely common, and this is essentially the entire controls system is this. So imagine I have a system. This could be anything. Could be an electrical system, could be a mechanical system, could be a car. And we usually have a lot of measurements from the system using a variety of sensors. The information from the sensors often goes to some kind of controller. In modern systems, this is usually a computer of different levels of computational power. Nonetheless, a computer runs some control algorithm and decides what inputs it needs to be supplied to the actuators of the system, and these actuators derive the system. So this is the essence of feedback control systems. And in simple conditions, when everything is linear, we can really simply represent this with our block diagram. Yes, block diagram. So this is my system, described by the transfer function G. It receives some input and produces some response output. This physical output might go to the sensor. Sensor might have its own dynamics. So for instance, you can think of it this way, that a physical thing happens. For instance, the temperature changes, the position changes, but the sensors read the output signal, for instance, the voltage or some digital information sent to the computer, might actually be a little delayed, or it takes some time to reach to its final value. So it may have its own transfer function, G2. And this output is the information that is sent to the computer. So the computer may have its own dynamics within its calculations. So depending on what input is, it can do some calculations and produce some output. So this is controller. Controller that sends the signal to the actuator. The actuator may have its own dynamics. For instance, when you supply voltage to a motor, the torque or the angular velocity or any other output of the motor takes some time, and usually with a certain profile or dynamics to reach that set point value. And this is my closed loop control system. Well, often the dynamics of the sensor is sometimes ignored, sometimes included within the block of the controller. Same for actuators, sometimes it is ignored, assuming that the actuator can instantaneously and exactly follow the set point or the required signal. Sometimes it is included as within the dynamics of your system, or sometimes in the controller. And maybe a bit of terminology, I wasn't planning on this, but this is often the system that we are trying to control is called the plant. And the rest of it, depending on how you want to group these together, constitute the controller. So this system has its own what is called closed loop dynamics. So the overall G, so it doesn't take any explicit input output. So everything is oh no, this is not, I shouldn't have drawn it this way. This is usually the output that we desire, and the input is kind of virtual here. It doesn't take any explicit input from the outside of this closed loop, and it has its own dynamics. You can think of it as a natural response. It will have a natural response due to the initial conditions of these systems. Another very common feedback control system actually takes an external input, and it is usually a reference that the system needs to follow. So we want my Y, the output of a system, follows a certain input, whatever input it is. So in those cases, this would be the block diagram of the system. So I have my input, I call it with, or show it as R. It goes to some addition, I'll get back to it later. The output goes to the controller with transfer function H. H defines what input needs to go to my plant or my actual system G, and then measurements of the output is taken and compared with the reference. So in this case, this becomes the error of the actual output of the system minus the response. This goes to controller, gives me X input to the system, and this is the closed loop system for controlling, closed loop block diagram for controlling the system to follow a reference set point. So let's look a little bit in detail here and see what we can do. So this E is my reference minus my Y, and X is this H times R minus Y, and finally Y is G times X, which is G times H, so I'm substituting this here, R minus Y. And if we rearrange, I have a GY here that can come here, so I have Y times 1 plus GH, Y times R plus GH equals GHR, or my closed loop transfer function, Y over R is going to be GH over 1 minus 1 plus, I think, yes, 1 plus GH. So this is the transfer function of the input-output relation from reference to output of this dynamical system. Given that I know my plant transfer function G, I can do two things. Either if I know what H is, I can fully know how my output responds to the inputs are, or often this is where we want to design a controller. We want to design my transfer function h of my controller such that this relationship, let's call it g of closed loop, this g closed loop behaves the way I want. So that is the general goal of control. And you can see with this very simple block diagram representation, we can start to think about how I can design a controller. So in this case, let me give you an interesting example. Do I have anything else? No. So when I say I want to design the controller, so often I have a robot. I work with robots. So this is my robot. I have a bunch of links, something like that. And in a class of control called impedance control, we want to make my robot to behave a certain way. And so imagine there is a robot moving around doing something, and I bump into the robot. So the way I want my robot to behave is I want it to have some kind of compliance. I don't want it to hit me and hopefully not kill me. So the way I like my robot to behave is I want it to feel like it is just a mass attached to this point. So if I want to grab this end and move it around, I want to feel that I'm moving around just a mass spring system. So this is called impedance control, and this is the closed loop transfer function of my entire system. I want it to behave like this. Now the question is, what is the h that can transform the dynamics of the system G into this new closed loop dynamical representation or transfer function? So that is one very practical way of thinking about designing these controllers and what I mean to represent the closed loop dynamics. So one other maybe piece of terminology that when we have these kind of closed loop systems, often the transfer function of the controller h is usually called gain, control gain, or just simply gain. So whenever you see the term gain, it means the transfer function that is in way of this feedback loop. And I also mentioned the possibility of having these different dynamics within the sensor dynamics or actuator dynamics. Those can have their own gains. So I think that's all I have for now. I don't have anything else. So we have started to use these transfer functions and the idea of transfer function to try to see better what we can do with more complex systems, both in terms of analysis. For instance, I want to know how my closed loop system behaves, or later on toward the end of this course, how I can use these to design controllers, to impose certain dynamics onto my system. So that's all for now, and Next time we will talk a little bit more about the analysis side, specifically the topic of stability. So until then.